everyone, welcome to GM Mini Lecture 3. Today we would cover modeling and statistical tests. My name is Claudia. I'm a senior majoring in statistics, and today I would be presenting this material with Jihi. Jihi, would you mind introducing yourself real quick?
Yeah, hi everyone, I'm Jihi. I'm a junior studying stats and CS, and in the second part of the lecture, I'll be teaching statistical modeling, and I hope you guys enjoy this lecture today.
All right, first we would cover statistical tests. Here are all the topics that we would cover for today: parameters versus statistic, and then correlation coefficient, hypothesis testing, bootstrap, p-value, confidence interval, and significance level, as well as A/B testing. Let's go through the first topic. So what is the difference between parameter and statistic? So parameter is a numerical measurement, but it describes the whole population. So for example, the average income of US citizen. On the other side, statistic is also a numerical measurement, but it's describing the sample. So for example, if we chose 50 US citizens at random, and then we try to find the average income of those people, then it would be statistic. Now here's just a difference notations between the parameter and statistic. For example, the mean, we would use mu to describe population mean, and x bar to describe the sample mean. And then standard deviation, we would use sigma to describe the population standard deviation, and small s to describe the sample standard deviation. And the size, we would use big N notation to describe samples, population size, and small n to describe the sample size. Now let's go through correlation coefficient. Correlation coefficient is a measurement of how strong a linear relationship is between two variables. So the more linear the relationship is between two variables, like this and this, the stronger the correlation coefficient would be. And we say that two variables has a positive correlation coefficient if an increase in one variable is associated with an increase in the other variable. And on the other side, if there's a decrease in one variable and an increase in the other variable, we say that the correlation coefficient is negative. Now we have to be careful when we are dealing with correlation coefficient, because it is only measuring a linear relationship like this. So if we have a curve, like a quadratic relationship, for example, it would not measure the relationship well. And also be careful when we are dealing with outliers like this or this, because outliers would drag our correlation coefficient significantly. So it would be best to take out all the outliers before we compute the correlation coefficient. Now let's go through hypothesis testing. So here are all the steps to do hypothesis testing. We would go through each of the steps one by one. The first step would be to formulate the null and alternative hypothesis. So the null hypothesis is basically saying that the data is randomly generated, and any pattern or variation that was found is purely due to chance. Meanwhile, alternative hypothesis is saying that there's something fishy going on there. So be careful when you choose your test statistic, because you want to make sure that a low or a high values would support your alternative hypothesis. So then you can compute the p-value easily later on. Now, after you have the test statistic, you can calculate the observed test statistic, which is basically just the statistic based on your original data set. And then after that, you want to simulate samples using your original sample, because you only have one sample set. And to generate more sample set, you just basically resampling from your original sample. A really common way to do this is using bootstrap. It's basically you resample from your original sample with replacement. So it's like rolling a die or like flipping a coin. So if you have like two blues and one red, it doesn't matter the number of blues and the number of reds, because it's with replacement. So you will always have the red available, and you will always have the blue available back again. So an example of resampling with replacement would be getting 3 blues from this original sample, or like getting 2 red and 1 blue from this original sample. After that, you would want to calculate the statistic for each of our resample, and then build a graph. Usually it's a histogram for our resample test statistics. After that, we want to compute the p-value. So how do you find the p-value? We actually use our observed statistic that we originally have, and then we put it on our graph, and then the p-value is just the percentage that is further from the null than the observed statistic. So if our observed statistics is over here and our null is over here, then the p-value would be this area that is further from the null. Now we're on our last step of hypothesis testing, which is the conclusion. In order to be able to conclude our test, we need to understand significance level, which is known as alpha, and confidence interval. So significance level is the probability of rejecting the null given that it is true. So it's an error, and we call that type 1 error. Meanwhile, confidence interval is the range of plausible value of our parameter. So what is the relationship between significance level and confidence interval? So we're saying that we are 1 minus significance level percent confident that the unknown value or our parameter falls in our confidence interval. So 1 minus alpha or 1 minus significance level is also known as the confidence level. So we would conclude to reject our null hypothesis if our p-value is less than the significance level. And we would not reject the null hypothesis if the p-value is larger than our alpha. Now let's move on to A/B testing, which is a special type of hypothesis testing that is checking whether two numerical samples came from the same underlying distribution. For example, you're given this data set, so you know whether the mom is smoking or is not smoking during pregnancy and the weight of the baby at birth. And you want to know whether maternal smoking is associated with the birth weight. Since A/B testing is a type of hypothesis testing, the guideline would match with hypothesis testing. So our first step would be to formulate the null and alternative hypothesis. The two samples in our case this time is the weight of the baby from smoking mother and the weight of the baby from non-smoking mother. So our null hypothesis would be saying that the distribution of these two samples are the same. And our alternative hypothesis will be saying that they don't come from the same distribution. The weight of the baby from the smoking mother are lower on average than the weight of the baby from non-smoking mothers. Next, we would choose our test statistics. So in this case, we are choosing the average weight of the smoking group minus the average weight of the non-smoking group. So a really, really low test statistic would be leaning towards our alternative hypothesis, which would make it easier for us to compute our p-value later on. And then we calculate our observed test statistic, and in this case, we got negative 2.096 ounces. After that, we would do resampling. But in this case, we don't do bootstrap. We're using another resampling method called random permutation using the shuffling method. So it's creating random sample with the same size but without replacement. So bootstrap is with replacement, and this time it's without replacement. For example, if we have 3 first record like this, for the maternal smoker, yes or no, and the birth weight. And then what we're gonna do, we're just gonna shuffle this label, the label for the maternal smoker, the true or the false. And it's gonna be like this. Since each of the label cannot be used twice, so it's without replacement, but we're generating a new sample from our original sample, so it's still a resampling method. And then now we would shuffle all the labels, get this new sample, and then calculate our sampling test statistic for each of them. And then the first one we got is negative 0.63 ounces. And then we would reshuffle 1,000 times. And then for each of them, we would calculate our resampling test statistic. Then we would build the graph based on our resampling test statistics. So we have like 1,000 of them. And then this is our graphs. And then what's happened next, we're gonna find the p-value. So how do you find the p-value? Remember that first we have to put in our observed statistic in the graph. So it's over here, it's negative 2.096. And then we would try to find the area where it is further away from the null, where it is leaning towards our alternative hypothesis. So as I said previously, when we define our test statistic, a really, really low number would be leaning towards our alternative hypothesis. So then we would try to find the area on the graph that is below our observed statistic, which means it is further away from our null hypothesis. And we can also compute that by just finding the number of simulated statistic that is less than our observed statistic over the number of simulations that we did, which is 1,000. In this example, we get 0.015 as our p-value. After that, we're going towards the conclusion, which is the last step of hypothesis testing. Remember that to be able to conclude our test, we need to define our significance level. In this case, let's choose 0.05 as our alpha. And since 0.05 is greater than our p-value, then we would reject the null. And we would say that the test support our alternative hypothesis, which is saying that the baby's birth weight from smoker mothers are lower in average than from the non-smoker mothers. That is the end of the statistical test. Now we're moving on to statistical modeling.
Thanks, Claudia. So let's get started with statistical modeling, which is a mathematical representation of the observed data. So here are the conceptual topics we will cover in the second portion: distributions, visualizations, quantitative variables, bar plots, histograms, and density curves. Now let's talk about distributions. What is a distribution? A distribution describes the frequency at which values of a variable occur. This means that all values must be accounted for only once, so the total frequencies must inherently add to 100%. Now let's look at this example. Is this a valid distribution? If you guessed no, you're correct. The reason this is not a valid distribution is because we see that the total percentage notated in the black numbers on the right sum to around 200% instead of 100%. And this implies that individuals were accounted for in more than one category, and this contradicts our definition of a valid distribution. How about this example? Is this a valid distribution? If you guessed yes, you're correct. Pretty simple, right? It's a valid distribution because we see that the total percentage of American adults in each income tier sums to 100%. So this means each individual appears in exactly one category. Now, since we covered the basic definition of a distribution, let's focus on visualizations now. Why do we visualize data? Well, there are two main reasons. The first is to advance our understanding of the data, and the second reason is to communicate our results and conclusions to others more powerfully. Here's another exercise. How many variables do you think we're encoding here? So let's go over this. Well, first we have the x and y variables, right? Okay, but we also have different sizes for each point and different colors. So we're essentially encoding 4 variables on this visualization. It's kind of interesting, right? So now let's visualize the relationships between quantitative variables. Most of you are probably familiar with scatter plots by now. We use them to reveal relationships between pairs of numerical variables, and we usually start with scatter plots to notice any obvious correlation patterns between data. We could observe a linear, quadratic, exponential, logarithmic, non-correlated pattern, and many more. We can also use color to encode categorical variables in a scatter plot. Notice how in addition to the two variables on the x and y axis, which are maternal height and birth weight, we also use color to graph by setting a hue to indicate whether each mother is a smoker. The blues indicate non-smoking mothers as opposed to the oranges, which indicate smoking mothers. So using color to introduce a third variable allows for more analysis. One thing to be aware is overplotting, which occurs when we plot too many points that it makes the visualization unclear. When this happens, the user cannot analyze the data clearly, so be sure to narrow down your data before you graph a scatter plot in order to avoid overplotting. Here we see two types of scatter plots. The left is a linear model plot, so we have a line of best fit using a regression model that goes through the scatter plot. This linear model is used to represent the general correlation of the data, and we notice how around half of the points are above and below the line. On the right side, we have a joint plot, which is a scatter plot, with two distributions of histograms on the top and right for each of the two variables on the x and y axis. This joint plot allows us to observe a deeper understanding of the distribution, such as shape, gaps, range, and mode of the data that we would not be able to see with the scatter plot alone. Now let's transition to bar plots. Bar plots are a common way to display qualitative or categorical variables, and the lengths are used to encode values, and color can be used to indicate a subcategory. Let's suppose we have a list of majors and a list of GPAs corresponding to those majors. This is a bar graph that would be appropriate for that representation of the categorical variables by major. But how about now? This colored bar graph is actually an improper usage of color because we are supposed to introduce color when we're introducing a third variable. However, here it is simply distinguishing the categories on the x-axis by major, but there was no need for that since we already have each bar segregated on the x-axis. Since color does not introduce any new variables in this example, its usage is meaningless and not a valid application. Now let's transition to histograms and density curves. Histograms represent the distribution of a variable by displaying the variable, such as weights in this example, on the bottom axis and the counts on the y-axis. Each bar represents the counts for each weight. So the sum of areas of the proportion of the bars should yield 1. We also use a density curve, which is a smooth curve drawn on top of the histogram, and this is used to visualize a continuous distribution of the discrete histogram. Similarly, the sum of the area under this density curve should also be 1, and this is how we yield the 68, 95, 99 empirical rule for the normal distribution of this curve. Here are some terms we need to know to describe distributions. So modes, which are local or global maximum, skewedness, tails, and outliers. A mode of the distribution is a local or global maximum. And so a distribution is said to be unimodal if it has one clear mode, bimodal for two clear modes, and multimodal for more than two clear modes. What describes the mode of the yellow distribution at the top? So this would be bimodal because it has two obvious peaks around 100 and 120. How about the bottom one? So this would be unimodal because it has one obvious peak around 120. Now let's talk about skewedness and tails. This diagram has a peak on the left side and a tail that spans across the x-axis on the right side. We call this a right tail, and distributions that have a right tail are skewed right. This basically means that the mean is greater than the median. In this diagram, more points are centered at the lower x values, which is the reason for the low median. However, we still have values along the tail on the upper x values. Though these values may be smaller in count, they weigh more because they're large x values. So, though the median is small and on the left side, Our mean is large and on the right. Thus, a skewed right distribution has a mean greater than the median. The same applies for a distribution with a long left tail. It is skewed left, and since the tail is on the left side now, the mean would be smaller than the median. If a distribution is roughly symmetric, then both tails are roughly of equal size. Now let's look at quartiles. Any data will have 3 quartiles. The first quartile for the 25th percentile, the second quartile for the 50th percentile, and the third quartile for the 75th percentile. So the interval between the third quartile and the first quartile contains 50% of the data, since it is between the 75th and 25th percentiles. We call this the interquartile range, and it is colored in blue in our histogram. Here's a translation of those quartiles onto a box plot. We have Q1, Q2, and Q3 pointing to the blue portion that spans the interquartile range. The tick marks at the end of the box plot are called whiskers, and each of these are computed by doing Q3 plus 1.5 times IQR for the top, and Q1 minus 1.5 times IQR for the bottom. Outliers are any values that exceed the whisker values. To go more in depth, we can overlay multiple histograms and density curves on top of each other for more insight. On the left, we see that this is a weak representation because the overlap is not clear. The middle one is improved since the density curves added to the histograms provide a more definitive outline of the shape. The right image has the clearest visualization because it only plots the density curves, which makes it the most clear to observe the contrast between the distributions. In conclusion, visualization requires a lot of thought. Here are some ways to break down which modeling to use. To visualize a single quantitative variable, we often use a histogram or a density plot. To visualize 2 quantitative variables, we usually use scatter plots, and for more variables, we overlay histograms and density plots. Pandas has a built-in plotting methods, but if you want more sophistication, you can always import Seaborn and Matplotlib, which are Python data visualization tools, and the links are here, and they're very straightforward to use. Yeah, so thanks for listening to Claudia and me today, and we hope you learned something new that you can apply to the project.